So, quick video on how to calculate the allele frequency of a population, which is a number that's important to us in studying evolution. Our definition of microevolution is a shift in allele frequency from one generation to the next, which I like to use as our actual definition of evolution because it's quantifiable. It is far less subjective than a change in an organism over time. And something we can measure, right? We can point it, we can say this is exactly how much evolution happened to this population in this generation. Cool. So our allele frequency is just an assessment of how much percent of a given gene pool is made up of each allele within that gene pool. Right? So I'm looking at gene A in this example. And for gene A, given it is a diploid organism, in a Mendelian trait, this only has 2 alleles for this trait. Right? If it's a multiple allele trait, you could line it up and have all of the alleles as well. Wouldn't change the math. It just makes an extra step or two. Okay? So I have homozygous dominant organisms, and in this population, I have 250 homozygous dominant organisms. I have heterozygous organisms, and in this population, I have 500 heterozygous organisms. And I have homozygous recessive, and in this population, I have 250 homozygous recessive organisms. It's important to remember that each organism has 2 copies of each allele. Okay? Yes. So, in my homozygous dominant organisms, okay, each individual organism has 2 big A's. So if I have 250 organisms and each has 2 big A's, that's going to be 250 times 2. Right? So this set, my homozygous dominant organisms, are contributing 500 total big A's to the population's gene pool. Okay? 250 times 2 is 500. Okay? So that's 500 big A's right there. My heterozygous organisms are contributing 1 big A and 1 little a. Okay? So if I have 500 heterozygous organisms, okay, with 1 big A each, that's 500 big A's, 500 times 1. Okay. They're also contributing the 1 little a, so that's 500 little a's coming from my heterozygous organisms. My homozygous recessive organisms are each contributing 2 little a's. So if I have 250 of those, that's 250 times 2 again. We have 500 little a's. So I add up all my little a's. I got 500 here. I got 500 here. That's a total of 1,000 little a's in this population. Okay. I add up my big a's. I got 500 here. I got 500 here. That's a total of 1,000 big a's in this population. Okay. Altogether, I have 2,000 a's. I have 1,000 big. I have 1,000 little. That's 2,000 a's. So to find the frequency of each allele, I'm going to take the number of that allele. So I have 1,000 big A's. I'm going to divide it by the total number of alleles in this population. So I take 1,000, I divide it by 2,000, and that gives me 0.50. Okay. I do the same thing for little a's. I have 1,000 little a's. I divide it by 2,000. That gives me 0.50. 0.50 is the same as 50%. Right? That is 50%. Okay. So my allele frequency is 50% big A, 50% little a. Okay? And then I would let this population mate, create the next generation. I would do the same math. and I would assess the allele frequency of the next generation. And depending on how much it's changed, I can see how much evolution has happened, how much I shifted towards one allele or the other. Okay? And I use that to measure whether there was a lot of evolution, a little bit of evolution. I can use that to compare different forces. Right? And so if I set up an experiment, I can apply natural selection to one population and sexual selection to another and see which one caused more evolution to occur. Right? Evolution is a hard thing to experiment with, but in the right environments, you can do it. Okay? So that's allele frequency, very important tool for assessing the amount of evolution that's occurring within a population. Awesome. You're welcome. Goodbye.